All right, so welcome to Math 150, Section 1, Lecture 7. We are now back in alignment because of Winter Carnival. We've now had 2 complete weeks, so now Mondays will be congruent to 1 Mod 3, which is nice. There were no comments about material people particularly want to see, so because of that, this is essentially going to be a bonus class. We're going to really talk about applications and why we use and why we need the stuff. So the big thing today was the definition of a partial derivative and the equation of a tangent plane. What do you think the tangent plane is generalizing? So the tangent plane is the 2-dimensional analog of what? Yes?
The tangent line.
The tangent line. So I want to do applications of the tangent line today. And I'm going to do it through the very famous birthday problem. How many of you have heard of the birthday problem? All right, this is a dangerously low number of people to do this with. I will potentially risk it. I really wish Kayla was here because every person really helps. So the question is, how many people do you need to have in a room before you have at least a 50% chance that 2 people share a birthday? Now, one of the reasons I love this problem is because as it's initially posed, it's poorly phrased. Can somebody give me an issue with how this is initially phrased? How many people do I need before I have at least a 50% chance that 2 share a birthday? Yes?
Well, you're excluding the year.
I'm sorry? So we're excluding the year. So I don't care if somebody was born in 1950 and somebody was born in 1970. I was actually had bad credit rating for a while because they amalgamated me with somebody who had 4 digits in common with me in their social security number. And the report had me born in 1950 and then again in the 70s. And I tried to argue with the credit card company, I was not born twice. So we're going to exclude, they don't have to be the same year. Okay, what else could be an issue? If I want to be able to make a good analysis of this problem. You want to try something? February 29th. Is there anybody here who was born on February 29th? So I actually have a deal with admissions that nobody born on February 29th is allowed to take my math classes because it just makes this problem a little bit more painful. So we will exclude. It is not a protected category. Date of birth is not protected. Okay? Also, being a Yankee fan is not a protected category. What else do we have to worry about? There's one other really big assumption. I want to try to calculate the probability that I don't have 2 people born on the same day. Or I want to calculate the probability that I do have 2 people born on the same day. What do I need to assume about people?
There's an equal chance that they'll be born on certain day.
Yeah, what could cause trouble?
If you're more likely to be born on, say, March 23rd than April.
Right, so if some dates are more likely to be birthdays than others. So the reason I like this is I don't want you to just get into the habit of just doing cookbook problems. I want you to really think about the problems you're looking at. You want to make sure you phrase it well. There is a great book by Malcolm Gladwell called Outliers. I will send you a snippet of it where he goes through and he takes the Canadian Junior Hockey League championship game from some year and replaces the names of the players with their birthdays. It's like January 7 has the puck, passes to January 14, January 14 passes to February 9, February 9 shoots, blocked by March 7. And just goes, and you see all these birthdays are clustered around a certain time of year. And the reason is when you're young, you want to be old enough to just miss the cutoff to make an age bracket. Because then you will almost surely be one of the larger kids in your age bracket. You'll look better. The coaches will play you more. You'll be nominated for more things, and it just propagates. And it's incredible to see how this happens in professional sports. So we want to assume all birthdays are equally likely. In particular, if we have identical twins at an event, very likely that there will be 2 people sharing a birthday. So my question is, under these assumptions, and again, this is why I really like the problem, is to think about what you need to solve it. How many people do we need? How many for a 50% chance that 2 share? And so here are the possibilities. Let's say on the order of 11, 22, 45, 90, 180, 360, 720. All right. So can anybody tell me any answers that seem, which do you think is the closest? Give me one that's really bad. Yes.
720, because you don't even have 720 days in the year.
We don't have 720 days in the year. So do we all agree that 720 is way, way, way too high for how many people I need for a 50% chance? All right. Somebody else eliminate something.
360.
360. Why?
Because it's only a 50% chance, and like that would make it pretty much 100.
Yeah, with 360, you almost are guaranteed. How many people do you need to be guaranteed? Okay.
Like 365 or 66.
366, because we don't allow February 29. So once you have 366 people in the room, clearly you have to have 2 people sharing a birthday. So 360 is almost surely. What about 180?
Yeah.
So do you think that the 50% is around 180?
Yeah, because basically there's 360 days if you divide that by 2. What?
So if you divide that by 2, so how many people like 180 as the answer? So what's wrong with Cam's argument?
Oh, wait, yeah, there's
I mean, the argument seems pretty good. 180 out of 360, that's about a half. Why is that not a good argument for 50% that 2 people share? Because at this point, it's the probability that as a new person enters the room, that person has a 50% chance of matching someone else. So at this point, if you haven't gotten a match, then it's extremely likely that the next person gives you a match. But you're quite likely to have already gotten the match before you get here. So this is probably too high. Now it starts getting a little bit harder into here as to exactly what's the right answer. So what I want to do is I want to show you how to solve this problem exactly. I want to show you why it's difficult to solve it exactly. I want to show you how calculus, in particular, how tangent lines help. And then the tangent plane is just the 2-dimensional generalization. Right? So the probability that in n people, none share. Right? It's sometimes easy to calculate the probability that something doesn't happen, and then the probability that it does happen is just 1 minus that. This is the law of complementary probability. If something has a 70% chance of happening, it has a 30% chance of not happening. If you have just one person, what is the probability that with one person in the room, you do not have 2 people sharing a birthday?
100%.
100%. We all agree it's 100%.
Yeah.
How should we write 100%? How could we write 100%? So one possibility is 1. There's a better way of writing 1. What number do you think is going to come into play for the birthday problem? Not 0.
66.
Well, we don't like February 29. Remember, 365. So what would the numerator be?
365.
Right. And now somebody had mentioned 0. I'm actually going to write it as 365 minus 0 over 365. Or, if you want, you can write this as 1 minus 0 over 365. There are 365 days available. Any day is good. Now let's calculate P2. The second person now walks in. What's the probability they don't share a birthday with the first person? So the second person walks in.
Is it 364?
It's 364. So the first person can have any birthday. Then the next person can't have that day. So I can write this as 1 minus 0 over 365 times 1 minus 1 over 365. Is the pattern becoming clear? If I had 3 people, it would be 365 times 364 times 363 over 365 cubed. And so if I have n people, it would be 365 over 365 times all the way down to 365 minus n minus 1 over 365. And I have to stop 1 earlier, because remember, I start off by subtracting 0. There's a certain person in the class right now who, when they were young, and I told them you can do something 3 more times, would always start counting at 0 and squeeze out an extra event. You want to be careful with your counting. My first one is 0, so if I have n people, I stop at n minus 1. I can write this many different ways. I could write this as 365 factorial over 365 minus n factorial, 365 to the n. And so this is the answer. And then what I can do is I can just see what value of n makes this 50%. Because what's nice is if there's a 50% chance it doesn't happen, there's a 50% chance it does happen. The problem with this is painful to do. If anybody has a calculator now, try to do 365 factorial on your calculator. Odds are it will overflow. If you have a better calculator, you might be okay. A lot of the older ones stop around somewhere between 60 and 80 factorial. The only way you can really do this on a calculator is you have to very carefully do the multiplication, division, multiplication, division, multiplication, division. You have to go very carefully down the line. It turns out that there is a generalization of the factorial function. We're not going to do too much with it now, but gamma of s equals the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx, and gamma of n plus 1 is n factorial. This is a really nice function. It's called the gamma function. And it begins to show you why calculus and real analysis can be useful. We can take a discrete function like the factorial, and we can replace it with something continuous. And we can use rules of analysis. So I could actually use this to evaluate. There are really good formulas to estimate numbers like this. Another way to write this, and this is going to be useful, a lot of what I'm doing now is to try to get us positioned for later in the semester, is Pn is the product, k goes from 0 to n minus 1, 1 minus k over 365. So you've hopefully seen summation notation before. What I want to do now is I want to try to use product notation. So this just means multiply everything out. Okay? So we've already talked about some of the really important techniques in analysis. So much of what we do is finding ways to look at algebra to see the relationships. We've talked about how you multiply by 1. And in fact, we already did a multiplying by 1 over here. I multiplied by 365 minus n factorial over 365 minus n factorial, so I could rewrite this in a nice way. We talked about adding 0. There's another technique. Whenever you see a product, you should have a Pavlovian response about something to do. What should you do whenever you see a product? Do you like products? Do you have experience with products? You've taken classes on Riemann products? No. You've taken classes on Riemann sums. You know how to deal with sums. How can you make a sum from a product? What can you do?
Distribute, like simplify it.
Well, if we expand this out, this would be a mess in terms of all the terms. So what do we have that converts a product to a sum? There is a function that does that. This function of a product is the sum of this function. What function is this?
The natural logarithm?
The natural logarithm. The log of a product is the sum of the logs. So if we take the logs of both sides, and to make life painful for you, once you get to college, you use log for the natural log, and you do not use ln anymore, because of course you're doing things base e. Why would you do things base 10? So log always means the natural. So the natural log of Pn is now the sum, k goes from 0 to n minus 1, of the log of 1 minus k over 65. This is an extremely powerful technique. Whenever you see a product, you should always think, let me take a logarithm. And now we're going to use calculus. It's been about 15 minutes. It's time to actually do some calculus. The idea is we don't expect k to be that large relative to 365. So what would be the easiest value of k to evaluate the log of 1 minus k over 365? What value of k would you love to take? So k goes from 0 to n minus 1. Which value gives you the easiest number to take the log of?
equals 0.
K equals 0. You've got the log of 1. What's the log of 1? 0. So the hope is that if k is very small relative to 365, this is approximately the log of 1 minus k over 365. Well, the log of 1 minus k over 365. Let me approximate it with the tangent line. So the log of 1 minus x, if you try to approximate it, you get negative x plus an error of size x squared. So if x is really small, the log of 1 minus x is approximately negative x. How do we do this? Well, we want to draw the tangent line. So let me come all the way down over here. So the way it works is, here's my point x naught. Here's my point x naught, f of x naught. And then here's my slope, f prime of x naught. And so now let's find the tangent line. So the tangent line would be y minus f of x naught is f prime at x naught, x minus x naught. For our problem, x naught is 0. Oh, sorry, x naught is not 0. X naught is 1. How would you? No, we're doing the log of 1 minus x. X naught is 0. F of x naught is the log of 1 minus 0. And what's the log of 1 minus 0? 0. F prime of x, I have to take the derivative of the log of 1 minus x. So I get a 1 minus x downstairs, and then I take the derivative of 1 minus x, and I get a negative 1. So then f prime at x naught is just x is now 0. I just get negative 1. So when I substitute here, I get y minus 0 equals negative 1 x minus 0, or y equals negative x. And that's the equation of the tangent line. So this should be a pretty good approximation to the log of 1 minus x. So now, if we substitute this in, we get the log of Pn should be approximately the sum, k goes from 0 to n minus 1, of negative k over 365. So this is now a good opportunity to review sums. We're going to have to do a lot more with sums later in the semester. When you see this, you see a negative 1 over 365. We can take that out, right? And so we get the log of Pn equals negative 1 over 365, and then the sum, k goes from 0 to n minus 1 of k. So this is a very famous sum. We're summing the first n minus 1 integers. So there's a story that when the great Gauss was in school, the teacher was just having a bad day and wanted to shut up all the brats, and said, add up all the numbers from 1 to 100. And was expecting to have a couple of moments to just relax. And Gauss immediately yells out the answer. How could you add up the numbers from 1 to 100 very quickly?
It would just be 101 times 49 plus 50. Wait, hold on.
You're very close. So I've got the numbers 1 plus 2 plus m. So add up the first m.
So it's m plus 1. Do I take the
So
first?
write them backwards.
Yeah.
So if you call this sum s, then you get twice s, m plus 1, m plus 1, m plus 1, m plus 1. How many times do we have it? We have it m times. You get m plus 1 is twice s. So s is equal to m plus 1 over 2. So this was Gauss's trick. It's absolutely beautiful. So it allows us to get an exact closed form expression for our answer. And so now, let's plug this in. So we're going to see how well the tangent line works. So we now have the log of Pn is negative 1 over 365. And now m for us, what value does n take on for our sum? For us, what would n be?
N minus 1.
It would be n minus 1. Now, our sum is starting at 0. Does it matter if we start at 0? No. Because if you add 0 to the sum, you're not changing it. So we would get n minus 1 times n over 2. And we want to choose n so that this Pn equals 1/2. Let n star be such that Pn star, that's going to be the critical value we want. So at that special point, we would basically have 1/2 is approximately negative 1 over, the log of 1/2 is approximately negative 1 over 365 n star minus 1 n star over 2. The log of 1/2 is negative log 2. I'm going to use some log laws, okay? The negative signs cancel. I'll move the 365 and the 2 over to the other side. I'll get 365 times 2 times the log of 2 is approximately n star minus 1 times n star. Okay, how could I solve for n star? What could I use? What could I use to solve for n star? What kind of equation is this in terms of n star? It's a quadratic. So we could use the quadratic formula. I don't want to do that. I'm going to either approximate this as n star squared, or if you want to do a little bit better, n star minus 1/2 squared. So take the midpoint of this, and you get 365, the log of 4, I'm going to just move the 2 inside the log of 2, is approximately n star minus 1/2 squared. Because if you expand this out, you'll get n star squared minus n star plus 1/4. And if you expand this out, you'll get n star squared minus n star. So they differ by a small amount. This is a pretty good approximation. So when I'm done, I get n star, my special value, triple star, is approximately equal to 365, the log of 4. I got to take a square root of that, and I have to add 1/2. And that is approximately the answer. Okay? So this shows you potentially the power of calculus. This is doing a tangent line. And we're doing the tangent line for a real-world problem. If you think nobody cares about people having the same birthday, you're right. But the math behind this is the same math that's used in a lot of crypto attacks. They actually call it the birthday attack. Trying to see when things align, how far do you have to go before things align. We don't want to deal with complicated functions. Do you want to deal with that product? Do you want to deal with a sum of logs? No. And the idea is we can replace this. So we have this answer. What would you like to know about this answer? So I'm claiming this is the answer. What would you like to know?
What it equals?
So one thing is what this equals, so we can actually do the calculation. And so in an entirely surprising moment, I actually have my computer here with this already loaded up. And so what we get is 22.9944 for the approximation. The actual value, when there are 22 people in the room, you have a 52.4% chance that everybody has a distinct birthday. When there's 23 people, it's 49.27% that everybody has a distinct birthday. This approximation, cover your ears, Kim, does a damn good job. Okay? It's phenomenal how well this does. I could do slightly better if I wanted to use the quadratic formula. If I wanted to do better than the tangent line approximation, I could try keeping the next term here. but the increase in accuracy is going to be so small, it's just not worth it. How many planets are there in the solar system? Yes. 8. Is anybody old enough to remember when there were 9 planets other than myself? Okay. So Pluto has been downgraded. I do not like the fact that Pluto has been downgraded. So I will single out Pluto today. It takes about 90,500 days for Pluto to go around the sun. So imagine we played this on Pluto. How many people do you think you would need before 2 people on Pluto have the same birthday in a row? A lot. What do you think would change from our answer? So let's look at our answer. If you had to just make a quick guess, what would change for our Plutonic friendships? Yes?
So 365.
That's why I was very careful not to multiply the 365 out. So if you have D days in the year, our guess is if D days in a year, we guess the square root of D times the log of 4 plus 1/2. So on Pluto, with 90,500, this would predict 354.2 people are needed. The actual answer is 354.47. It is amazing how well this does. So I really want you to see the applications of the tangent line and more generally the tangent plane. It's very easy to just have so much material coming at you that you just memorize it, you regurgitate it, you pass the class, and then you never use it again. The idea is we want to develop math to solve problems. And the point here is we want to take very complicated phenomena and we want to try to isolate the key features. How many of you are considering economics? So if you want to do anything in quantitative economics, you have so many variables going on. It's going to be really hard to get a sense of what's going on. You want to find ways to which are the ones that really matter and come up with a simplified model. All right. Any questions on the birthday problem? I will try to end class early so we can try to see if we actually have a match here. Based on the enrollment of section 1, I'm not optimistic. Right? I have less than a 50% chance. Missing Kayla really hurts today. I've never done a class where this has failed, however. My favorite was the first year I was teaching at Williams. I didn't succeed until the last row when I had 2 people sitting next to each other who shared a birthday. And I actually carded them just to make sure they weren't doing this to make me feel good. I will send you the Mathematica code to do this analysis. What's interesting is Mathematica has a find, has a numerical solve command that is not able to find the correct values for this. So what I did instead of using solve is that Mathematica has a find minimum. So I looked at the product minus 1/2 and squared it and said, where is that smallest? And that's equivalent to finding where it's closest to 1/2. A lot of times you have to figure out how do I massage things so that it fits what toolbox I have. I don't know if I've shared with you yet, but my favorite quote is, if all you have is a hammer, pretty soon every problem looks like a nail. If you know how to do something well, whatever you're given, you convert it to that. Okay. So let's talk now a little bit about differentiation. And so what was the Michael Jackson song that was played at the start? Man in the Mirror. And what are they talking about in that song?
Well, it's like reflecting on ourselves, we can like change.
So you can change. So I thought that would be a good way to start talking about derivatives, the rates of change. All right. So definition of derivative. You are used to the following. F prime of x is the limit as h tends to 0 of f of x plus h minus f of x over h. That's one way to define the derivative. Another way is f prime at x naught is the limit as x approaches x naught of f of x minus f of x naught over x minus x naught. Just view x as x naught plus h. So if I write my derivative like this, it's really the same. What we're going to do now is we're going to do another way of looking at the derivative. I want to look at f of x minus f of x naught minus f prime at x naught of x minus x naught divided by x minus x naught, and take the limit as x goes to x naught. What should this equal if my function is differentiable at x naught? Well, if my function is differentiable at x naught, what does this part over here look like? This part will just look like what?
Derivative.
Yeah, this will just look like f prime at x naught. And then I'm subtracting out f prime at x naught times x minus x naught divided by x minus x naught. So I'm subtracting off f prime of x naught. So what should this limit equal?
0.
0. So this is another way of defining the derivative. The derivative is that number, which I will denote f prime of x naught, such that this limit equals 0. Okay. How can I view this? What I'm saying is if I take my function and I subtract off the tangent line approximation, it's going to be so close that even when I divide by how much I've moved, it still tends to 0. That's the way to view what we're doing. Okay? That's a really good way to view what the derivative means. When you subtract off the tangent line approximation, you are so close that even on the scale at which you're looking at, the difference is small. If x is close to x naught, then the numerator should be small. But small relative to what? Small relative to how much I've moved. You would actually hope that this, if the function is twice differentiable, it would be of size x minus x naught squared. So if x minus x naught is 1 over 100, the difference would be on the order of 1 over 10,000. Okay? So now when we talk about what does it mean for a function of several variables to be differentiable, it's going to be more involved. And the reason it's going to be more involved is we need some kind of notion like this. We have to be very careful that no matter what path we approach, we want to get 0. So what I want to do now is I want to take the time to look at some really painful limits to just show how things can go wrong. So let's look at the limit as xy goes to 0, 0. Oh, let's hope I can remember this correctly. I think x to the 8th plus y to the 8th over x squared plus y to the 8th minus x to the 10th plus y to the 10th over x squared plus y to the 10th. I believe that's what I want to look at. What do you think about this limit? What should we do? What's your Pavlovian response when I give you a limit question? Well, we can't just plug in 0, 0, because we're trying to have xy approach 0, 0. Yes?
You plug in 0 for y.
So the first thing is let's approach along the x-axis. And after we approach along the x-axis, what should we do? Approach on the y. So if we take the path y equals 0, all right, so if y equals 0, x to the 8th divided by x squared, that's x to the 6th, x goes to 0, so what does that go to? 0. And over here, I have x to the 10th over x squared, that's x to the 8th. Okay, so that goes to 0. So does everyone agree that along the path y equals 0, we get 0? All right? Let's take the path x equals 0. We have y to the 8th over y to the 8th. What's y to the 8th divided by y to the 8th? 1. Good. And as y goes to 0, what does 1 go to? 1. Right, Cam? Does it change? No. All right? So we'll get 1. What about this side? We get y to the 10th over y to the 10th. 1. 1 minus 1 is 0. All right, how many people think the limit exists? I've only done 2 paths. Let's do a straight line. Let's try y equals ax. So we now get the limit as x goes to 0. Now when y equals ax, we get x to the 8th plus a to the 8th x to the 8th. So we'll get 1 plus a to the 8th x to the 8th. And then down below, we will get x squared plus a to the 8 x to the 8 minus 1 plus a to the 10 x to the 10 over x squared plus a to the 10 x to the 10. Ah, okay. This is a little bit more involved. Well, this is an x to the 8. What goes into the denominator? What could I pull out from the denominator? An x squared. So if I pull out the x squared, this is now just 1 plus x to the 6th. And similarly over here, I can pull out an x squared. Ah, what does this expression go to now? Where does the denominator go to as x goes to 0? It would just equal 1, because good, this part goes to 0. 1 plus a to the 8, that just goes to 1 plus a to the 8. And I have an x to the 6th. So what does the numerator go to? 0. So we have 0 over 1, which is 0. Over here, we've got 0 over 1, which is 0. So the limit is 0. So I've shown the limit is 0 along every straight line. Are you now convinced that the limit is 0? All right, this is like going to my son's 5th grade class. They know me too well at this point. All right. So you are suspicious. You want to try along a parabola. Will that convince you? If I show it works along parabolas, that's not going to convince you?
I don't even know what that is.
It's along the line y equals x squared. So wherever you see y, you replace x squared or x equals y squared. So you could try parabolas, and you would also get a limit of 0. But let's try x equals y to the 4th. Let's try that path. This is a quartic. You would then get the limit as x goes to 0. Now the first piece, x is y to the 4th. We would get y to the 32 plus y to the 8 over y to the 8 plus y to the 8, which is going to be 2y to the 8, minus y to the 40 plus y to the 10 over y to the 8 plus y to the 10. I've got a y to the 8 down here, y to the 32 plus y to the 8. So I can pull out a y to the 8. This is the same as the limit as x goes to 0 of y to the 24 plus 1 over 2. And now here I have a y to the 8. So I could have a y to the 32 plus y squared over 1 plus y squared. I'm sorry, I want y going to 0, not x, sorry. What does y to the 24th plus 1 over 2 go to as y goes to 0?
1/2.
1/2. And what does this go to?
0.
0. We get 1/2, which is not 0. So for those of you who know me well enough now to be suspicious, you were right to be suspicious. The limit does not exist. But it exists if you go along straight lines, any straight line. It exists along quadratics. I think it also exists along cubics. It does not exist along a quartic. This goes back to the Miyagi's secret of multivariable calculus from the Karate Kid 2. You have to check every single path. Just because I check a bunch of paths doesn't mean it works. This is the theory behind why we have all these results in the textbook about the need to have the partial derivatives continuous, and this is why this is the correct definition. That's why this is the correct definition of the derivative in several dimensions. We need to have a good tangent plane approximation. It's not enough to say things are good along the x-axis, then things are good along the y-axis. Okay? So I think in the video, we look at the cube root of x times y. I think that was the problem that was looked at. That's a really good function to look at. And so when you start doing partial derivatives, that will have partial derivatives of 0 along the x and the y axes, but not in general. So we need a good definition of the derivative. And it all comes down to the difficulty of working with limits. This was not fun, that problem. It's somewhat fun to construct pathological examples like this to make your students' lives miserable. But you have to be careful. We want to make sure something like that doesn't happen to us. And that's where, if the partials are continuous, everything is okay. So partial derivatives. So we say df dx is going to be the limit as h goes to 0 of f of x plus h comma y minus f of x y over h. And that will be taking the derivative of f with respect to x. We sometimes write this as f sub x. Okay? Sometimes we might write things in vector form. We might write df dx is equal to the limit as maybe h goes to 0, f of my vector, v plus h e1 minus f of v over h. And the advantage of doing something like this is I'm being very careful. Here's my direction, and here's my magnitude in the direction. I can't divide by he1. I can't divide by a vector. I can't do vector divided by vector. I have to do lengths. Now, if I write fxy, it's initially not clear what that means. Does that mean first take the derivative with respect to x and then y, or first take the derivative with respect to y and then x? It's first take the derivative with respect to x, then take the derivative with respect to y. So it would be the partial with respect to y of f of x, or the partial with respect to y, the partial with respect to x. If life were good, what would you like f sub xy to equal? So taking the derivative first with respect to x and then with respect to y would be the same as what if life were good?
0?
Nope.
fyx?
You would hope that it would be the same as fyx, that the order in which you take the derivatives doesn't matter. Differentiate with x, then y, or y, then x, doesn't really matter which way you do it. Okay? Unfortunately, that's not always true. And that's why we have conditions in the book and theorems as to when can you switch the order of differentiation and have the result equal. So I brought Rubik's Cubes in on the first day of class. Rubik's Cubes are a great example of if you do moves, the same sequence of moves but in a different order, you will get to a different state. That often order matters. So here we have our notation. The last bit of notation is the gradient of f. So this is gradient of f. This is going to be df dx1 df dxn. Okay? So what you're doing is you're constructing a vector whose components are the partial derivatives in a very special choice of directions. In the x-axis, in the y-axis, in the z-axis, or in general in n-dimensional space, in direction 1, direction 2, direction 3. We can always construct a vector like this. The question is, when does this give rise to a function that is differentiable? And this is where, as I said, there's this big theorem in the book that if these partials are continuous, then you can get anything. Now, I like the vector definition here, because this is saying, take our vector v and move in the direction of e1 h units. Well, instead of moving in the direction of e1 or e2 or e3, maybe I could move diagonally. Root 2 over 2, root 2 over 2, at a 45-degree angle. And this definition here naturally generalizes to taking the derivative in any fixed direction. In a surprise, we actually have a good name for this. It's the directional derivative. And we'll get to that later in the semester, and we'll see how you can calculate the directional derivative from knowing this. Okay? But right now, we're only taking derivatives in special directions. And then we're forming a vector like this. And the hope is that this vector will encode what's going on. And there's notation in the book and in the video on what it means to write down df, the full derivative, which is basically the same as the gradient. And now we want to write down the tangent plane. So we'll often do this in 2 dimensions. So we might have z equals f of xy. And we want to try to come up with a tangent plane approximation to this. And what did we say the tangent plane is generalizing? So what's the tangent plane generalizing? Oh, sorry? Okay, what's the tangent plane generalizing?
Tangent line.
The tangent line. So whatever we get for the tangent plane, somehow it should reduce down to the tangent line if either x or y is held constant. So let's say we have z naught is f of x naught, y naught. That if I hold y constant, I should get z minus z naught is the partial with respect to x, and I'll put over here x naught and y naught to just tell me what point I'm evaluating this at, times x minus x naught. This is the tangent line approximation if I consider y as a constant. That's what we did earlier when we did the birthday problem. Well, if instead of considering x constant, I could consider y, instead of considering y constant, I could consider x constant. And then all that would change is this would become a df dy, y minus y naught. So the very natural guess for the tangent plane, df dy at x naught, y naught, y minus y naught. And this will be the equation of the tangent line, the tangent plane. It's the only thing it can be. It's got to be something that will reduce to one-dimensional tangent lines. And so you can see it's going to reduce. And now if you want, we've got like a minute or 2 left, we can rewrite this in terms of the equation of a plane that we're more used to seeing. So we're used to the equation of a plane. Normal dotted with x, y, z equals something fixed, right? And so you can see what the normal vector is going to be here. The normal vector would be df dx, df dy, and then -1. And that will be our equation, that will be our normal vector. And so here we're considering z as a function of x and y. So our surface z is giving us the height of how far above we are. Okay? Any questions on what we've done? So we're beginning to see applications. We're beginning to see that the techniques we're developing can be used for a variety of problems. Right. I'm going to turn the lecture. Yes?
Why is it z equal -1?
Because if you look at what's going on here, I have z minus z naught. So if I want to bring this over to the other side, it would now have a -1 times z minus z naught. All right. We have 1 minute left.